In physics, self-organized criticality is a property of dynamical systems that have a critical point as an attractor. Their macroscopic behavior thus displays the spatial or temporal scale invariance characteristic of the critical point of a phase transition, but without the need to tune control parameters to precise values. The concept was put forward by Pabak Chow-Tang and Kurt Wiesenfeld in a paper published in 1987 in Physical Review Letters, and is considered to be one of the mechanisms by which complexity arises in nature. Its concepts have been enthusiastically applied across fields as diverse as geophysics, physical cosmology, evolutionary biology and ecology, bio-inspired computing and optimization, economics, quantum gravity, sociology, solar physics, plasma physics, neurobiology and others. SOC is typically observed in slowly driven non-equilibrium systems with extended degrees of freedom and a high level of nonlinearity. Many individual examples have been identified since BTW's original paper, but to date there is no known set of general characteristics that guarantee a system will display SOC. Overview. Self-organized criticality is one of a number of important discoveries made in statistical physics and related fields over the latter half of the 20th century. Discoveries which relate particularly to the study of complexity in nature. For example, the study of cellular automata. From the early discoveries of Stanislaw Ulam and John von Neumann through to John Conway's Game of Life and the extensive work of Stephen Wolfram, made it clear that complexity could be generated as an emergent feature of extended systems with simple local interactions over a similar period of time. Benoit Mandelbrot's large body of work on fractals showed that much complexity in nature could be described by certain ubiquitous mathematical laws, while the extensive study of phase transitions carried out in the 1960s and 1970s showed how scale-invariant phenomena such as fractals and power laws emerged at the critical point between phases. However, the term self-organized criticality was firstly introduced by Bach, Tang and Wiesenfeld's 1987 paper, which clearly linked together these factors. A simple cellular automaton was shown to produce several characteristic features observed in natural complexity, noise and power laws, in a way that could be linked to critical point phenomena. Crucially, however, the paper emphasized that the complexity observed emerged in a robust manner that did not depend on finely tuned details of the system. Variable parameters in the model could be changed widely without affecting the emergence of critical behavior. Thus, the key result of BTW's paper was its discovery of a mechanism by which the emergence of complexity from simple local interactions could be spontaneous, and therefore plausible as a source of natural complexity, rather than something that was only possible in the lab where it was possible to tune control parameters to precise values. The publication of this research sparked considerable interest from both theoreticians and experimentalists, and important papers on the subject are among the most cited papers in the scientific literature. Due to BTW's metaphorical visualization of their model as a sandpile, on which new sand grains were being slowly sprinkled to cause avalanches, much of the initial experimental work tended to focus on examining real avalanches in granular matter, the most famous and extensive such study probably being the Oslo Risopile experiment. Other experiments include those carried out on magnetic domain patterns, the Barkhausen effect and vortices in superconductors. Early theoretical work included the development of a variety of alternative SOC-generating dynamics distinct from the BTW model, attempts to prove model properties analytically, and examination of the necessary conditions for SOC to emerge. One of the important issues for the latter investigation was whether conservation of energy was required in the local dynamical exchanges of models. The answer in general is no, but with reservations, as some exchange dynamics do require local conservation at least on average. In the long term, Key theoretical issues yet to be resolved include the calculation of the possible universality classes of SOC behavior and the question of whether it is possible to derive a general rule for determining if an arbitrary algorithm displays SOC. Alongside these largely lab-based approaches, many other investigations have centered around large-scale natural or social systems that are known to display scale-invariant behavior. Although these approaches were not always welcomed by specialists in the subjects examined, SOC has nevertheless become established as a strong candidate for explaining a number of natural phenomena, including earthquakes, solar flares, fluctuations in economic systems such as financial markets, landscape formation, forest fires, landslides, epidemics, neuronal avalanches in cortex 1, noise in the amplitude envelope of electrophysiological signals, and biological evolution. These applied investigations of SOC have included both attempts at modeling and extensive data analysis to determine the existence and/or characteristics of natural scaling laws. The recent excitement generated by scale-free networks has raised some interesting new questions for SOC-related research. A number of different SOC models have been shown to generate such networks as an emergent phenomenon, as opposed to the simpler models proposed by network researchers where the network tends to be assumed to exist independently of any physical space or dynamics. Despite the considerable interest and research output generated from the SOC hypothesis, there remains no general agreement with regards to its mathematical mechanisms. Baktang and Wiesenfeld based their hypothesis on the behavior of their sandpile model. However, this model was subsequently shown to actually generate 1f2 noise rather than 1f noise. Other simulation models were proposed later that could produce true 1f noise, and experimental sandpile models were observed to yield 1f noise. In addition to the non-conservative theoretical model mentioned above, other theoretical models for SOC have been based upon information theory and mean field theory, as well as a mathematical convergence effect related to the central limit theorem based on the Tweedy distributions. But no particular model explaining SOC has found general acceptance. Examples of self-organized critical dynamics, in chronological order of development: Baktang-Wiesenfeld sandpile, forest fire model, Olami-Fader-Christensen model, Bax-Nepen model.